So I swear at some point I just have to stop saying that I'm going to do these YouTube videos. At some point I just have to stop saying that I'm going to do these YouTube videos and actually do them. Boy, I often say this, that I'm going to start a YouTube series and I can never decide exactly what I want to do. So I know that I like to game, but I also know that I like to do computer sciencey stuff because I am a massive nerd. And so tonight I think that I'm going to record my first video, and I'm actually going to try to publish it this time, and I'm going to try to make it work. And this video is going to be on logic gates, and it's going to be the first in a little mini series that I'm going to do on building a simple microprocessor inside of a piece of design software. So this piece of software that I have open right here is called Digital. This is a logic simulator, and you can see that we can add components. Here, I will open the component tree view. So we have these components in the side here, and these are all the different options that we can add to a logic circuit over here. And you can see that we have clock inputs, and we can have dip switches, and they just toggle on and off, and I'm not going to be able to do anything with them at the moment because I don't have anything connected. Let's see here. Digital has kind of an odd layout. Alright, so just connect a few simple things up so you can see exactly what we want to do. And things behave just as much as you would think that they would, with the different switches and the different displays and things like that. That's one that you have to add a decoder to. I want to do a 7-segment hex display because it's a little bit easier to work with. I'll put on a couple more dip switches. And I'm just going to show you the basic idea of how digital works. And then from there, I'll kind of start into the topic that I want to go on tonight. So this is a splitter. And we can set the number of wires in and out. And actually, we'll do that. And let's go there. And start going to tie that to a constant 0. And this is just going to give you an idea of how this works. So the main digital window, you add components to your circuit here. Obviously you have the component tree over here, and most master windows will start with this component tree view. You can opt to start with it or not. I usually opt to start my main window with the component tree view. Sorry, if you guys have not joined me by pouring a pint of Guinness yet, you're going to want to do that now. First thing that you need to do when you open Digital is pour your Guinness. That is the first thing you need to do. So we'll go ahead and pour the rest of that. And yeah. Yep. Okay. So again, this is the main digital window. Add components here. Fetch components from over here. You can zoom in and out of the circuit. You can reset the zoom level. Well, actually, I don't think that resets the zoom level. It fits it to the window. You can do that. Naturally undo, redo, delete buttons. Say pretty much all the normal editor stuff. Then there's these simulation buttons up here. Before I move on to what these buttons do, I'm going to show you one other piece of software. This piece of software is called Logisim, and Digital is actually built off of Logisim. And Logisim is also a circuit simulating software, but you can see that Logisim actually, the simulation is always running for Logisim. And you disable it and enable it. Whereas with Digital, it has a little bit of a different way of simulating things. I'm not exactly sure what the difference is. It's kind of techy and more than I really ever wanted to get into, so I don't really mess with it much. But it has more of a sophisticated simulation, and so its simulation is disabled until you hit the run button. So now the simulation is enabled, and you can see that if I pulse the clock input, that I'll get this light to light up. Same with the dip switch. If I turn the dip switch on, the light comes on. If I turn it off, it goes off. And I can set different numbers, and if I set them in binary, so let's count upward in binary real quick. So we'll do 1, 2, 3, 4, 5, 7, 8, 9, oops, 10, A. This is hex. B, C, D, E, F. Alright, so we just counted upward to 16, well 15 technically. And yeah, so that's how the digital window works. And I think that's about all that I have to say about the piece of software itself. It's a really, really handy circuit simulation software, and I'm going to go ahead and open one for you now. I'll discard this. I'm going to open... let's open the 4-bit micro. This is just a little microprocessor that I built, if it's going to work. This is just a 4-bit microprocessor that I kind of built. It's not done yet. But this is an example of the things that you can do with digital. I don't know if this is going to actually do anything at the moment or not. So I'll reset everything, and then I'll turn the power on. The system clock is running. I don't think there's anything in the memory, though. Yeah, so there's nothing in the memory right now. So it's not going to do anything, I don't think. Actually, it may be waiting for a keyboard input right now. I don't know why I typed dad. I certainly didn't mean to. So actually, yeah, it did. It's consuming the characters off of the keyboard. Alright. So this does actually work. So if I go ahead and stop this. So I do have a piece of software programmed into it right now, surprisingly. But I don't have it set to start a real-time clock. So I'm going to start a real-time clock at 20 hertz. And then you're going to see that if I type in that again and then I hit the power button, that it will consume those characters off of the keyboard, or at least it should. Maybe not. I don't understand why it was taking them earlier, but it's not taking them now. That's weird. Okay, well, anyway, this is an example of something that you can do with logic, or with digital. This is not where we're going to start out, obviously. This is going to be something that we build up to. But I'm going to go ahead now, and I'm going to restart the simulation window. Well, I'm going to open a new window anyway. Discard the changes there. And now we have a fresh window open. Okay, so before we go any further here, I'm going to throw a little bit of history at you, and we are going to delve into the world of Boolean logic. Now, Boolean logic can be thought of as the fundamental building blocks of what we think of today as modern computers. Boolean logic is a system of representing logical operations and applying those to mathematics. So Boolean logic was derived, well, it was thought up by a man named George Boole, from which we derive the name Boolean logic. He wrote a book in the year 1847 called The Mathematical Analysis of Logic. And what George Boole thought was that mathematics would be a better foundation for the premises of logic than language would be. It would be more descriptive of logic. And it's true that mathematics, in a way, is simpler than language, especially when you boil it down to a certain level. So he wrote the book in 1847, and then other men took it a little bit further and applied it to different forms of mathematics. But actually, George Boole was a self-educated man, which is rather impressive to come up with some kind of system like this and be self-educated. That's pretty impressive. So from George Boole, we move into John Venn. He was the man that was behind the Venn diagrams that we all are so used to seeing. And he is the one that took Boole's equations and he formed the first system of symbols that represent the logic operations that we know today. And he extended Boolean logic to include other areas besides mathematics. And so there are a couple different notations for the different logic operations that Boolean algebra can satisfy, but John Venn was responsible for the very first one that was ever formed. And then lastly, and this is where we start to get into the practical application in the area of computing, was a man named Charles Sanders Peirce. And he wrote a paper that was titled On an Improvement in Boole's Calculus of Logic. And what he showed was that algebra could be performed using repeated binary operations. So what's a binary operation? Well, a binary number, and let me pull up a resource here. It is in here. In here. And we'll bring this up. And I'll bring it onto the screen for you. So, binary operations are really just a sequence of operations using binary digits. So all of us every day think in terms of decimal operations, right? So we all know that if we start at 0 and we start counting upwards, that we'll count as such: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Well, a binary system works the same way. You start at 0 and you count upward. There's a big difference, though. If you look at the decimal system, we have the numbers 0 through 9 that represent the possible values in a decimal system, whereas binary has only 2 values. So we have, altogether in a decimal system, we have 10 values. We have 10 symbols that represent values, correct? So we can count all the way up to 10 before we have to roll over into the next order of magnitude, or into the next decimal place, or basically until we have to start using another digit to represent what we want to see. So we can count all the way up to 9, and then all of a sudden this weird thing happens where we have to roll over and say that now we are at 1, 0, or 10 as we call it, because we can no longer use the values that we have to represent any higher values. So we roll the system over into the next place, and we end up with the number 10. And then you see that the sequence of counting just repeats, and we go 10, 11, 12, 13, 14, 15. And the same thing happens with binary, except in the binary system, we only have 2 digits that represent all possible values. So in binary, we start at 0, and then we go to 1, but now we're out of digits. So what do we do? Well, we roll over to the next place. So we end up with the decimal equivalent of 2. The decimal equivalent... Okay, let's start that over again, because I wasn't sure what I wanted to say. But the binary value 1, 0 is equivalent to the decimal value 2, because we've rolled over that place. So if we count 0, 1, we run out of digits, we move to the next place, we have 1, 0, and then we have another place to fill, so we say 1, 1, and now we've run out of digits again, so we roll over to the next place, and it's 1, 0, 0, and then 1, 0, 1, 1, 1, 0, 1, 1, 1. Oh, look at that, we ran out of digits again, we roll over to the next place, and so on and so forth. And I stopped this count at 15 because it rounds us out neatly to 4 bits of information. And whenever we discuss bits in a computer, this is exactly what we're talking about. Where bit is just an abbreviation of the word binary digit. Whereas we have decimal digit, we have hex digit, and a digit is just a way to represent a number or a numerical value. So we have now this series of bits, and we can count upward using these binary digits just the same way that we do in decimal. So that is why Peirce's application of being able to show that algebra can be performed using just these repeated binary operations, that was huge, because now we can take logical operations that just take 2 of these binary digits, and by comparing the 2 binary digits and putting out some output as a result of the 2 values, we can perform algebra that way. So let's take a look at the foundation of what Boole was trying to do and what kind of things he came up with. So I'm going to scoot this off again. May bring it back in later. I'm not sure if we need it or not. So what we have at the basis of every computer is logic. And we have this series of logic gates over here in the digital window that represent all the possible logic operations that we can take on 2 bits. So the first thing that we're going to do is we're going to pull out 2 bits, and we're going to do that by taking 2 dip switches. And these 2 dip switches represent 2 binary digits. We'll call them digit A, and we'll call it B. And now this represents two bits. So if we take 2 LEDs and we put them here, we can see, obviously, that when we start the simulation up, if we toggle the A bit on, that we get an LED lit, and if we toggle it off, we have an LED that's not lit. So that represents, back over here in our, where is it? There it is. Over in our binary chart, let's just arbitrarily assign this. So now we'll say that when the A switch is off and the LED is not lit, that represents a 0. And then when the A switch comes on and the LED is lit, that represents a 1. So, according to what Pierce discovered, we could somehow take these 2 values, put them through some kind of logic, and out the other side have algebra performed. Well, how do we do that? Well, that's what we're going to explore here in a minute. So we're going to keep our A and B inputs, and then we're going to start looking into the fundamental logic gates that make up Boolean expressions. So I have one more resource that I have to locate here. That is not the resource that I was looking for. It actually is the same resource. I don't know how I opened 2 copies. So we're going to keep this one over here, and we'll close the other one because it's resized and all weird. We're going to just not save it. And where is the file manager? And we'll go into here, here, here. Yeah. Alrighty. So, Boolean logic. So we have the fundamental logic gates that make up Boolean expressions. What do I mean by that? Well, we have different ways of expressing how 2 bits can be combined to make an output. And I'm going to go over, there are 3 fundamental basic types of gates, and then there are 3 derived types of gates that can be made from those 3 basic gates. And then there is a 7th gate that is the one that allows you to derive from the other gates, kind of. All the gates are important. All of them are fundamental building blocks, and all of them can be combined in certain ways to make Boolean expressions. Now, you can kind of think, if we sit and we think about logic for a minute, whenever we talk about things in real life, we may talk about if something, then something else. So we may say, if it's raining, and this is a high-level concept, and there's other factors that go into it in real life, but fundamentally we could say something like, if it's raining, wear a coat. Well, we could do something similar in using bits, right? So let's do something else here. So we have A, that's one of our inputs, right? So then we'll label this LED Q. And we're going to label it Q for a very specific reason. So what we're going to say is that if A is 0, then Q is 0. And if A is 1, then Q is 1. A is the input, Q is the output. So we can see that this little circuit right here demonstrates that concept perfectly. If I toggle A on, Q comes on. A is 1, Q is 1. A is 0, Q is 0. And we represent what's going on in this circuit or in this logic this little bit of logic with something called a truth table. And let me see here. I should be able to... Yes. Should be able to pull this up. And what we're going to do here is we're going to make a list of truth tables. All right. So, truth tables. So for this circuit, to make a truth table, all we have to do is this. We have a list of inputs on this side, and then on the other side we have a list of outputs, and then down here we just list their possible values. So let's start with the truth table for this little circuit right here. So we start with A and Q, and then we say for this truth table, if A is 0, then it follows that Q is 0. And if A is 1, then Q is 1. And we can see that this circuit satisfies that equation, this truth table. It satisfies this logic because as soon as I flip the switch on, Q comes on, and as soon as I flip the switch off, Q goes back off. So this truth table is satisfied by this first little diagram that I created up here. Now, what happens if we want something different? Well, say that maybe in real life we would say, if, let's see, let me come up with a good one because the raining one doesn't quite fit here. Oh, okay. If it's sunny, then I don't wear a coat. If sunny, not coat. So we're going to say that if A, then Q, we'll make another truth table, and we'll say if A is 1, it's raining, or if A is 1, it's sunny, then Q, I wear a coat, is 0. And if it's A, it's not sunny, then I wear a coat is true. So it's exactly the opposite of the original case. So is there a way to represent this in logic? Well, in Boolean logic, well, yeah, of course there is. We already knew that because we said that we can satisfy different logical equations based on Boolean logic. So what we have up next is the NOT gate. And the NOT gate just says that whatever is coming in as input, the opposite will come out as output. So we'll pull this little, or we'll start the circuit here, and then we will pull up this table again, and we'll see that the first condition, or the second condition is already satisfied, right? When A is 0, Q is 1, and then if we toggle it, it's exactly the opposite. We see that A is 1 here, but Q is 0, and we could tell because this line is light green. And you see when the line goes light green, then it means it's on. So now A is on, but Q is 0 because this gate inverts the input. It complements the input, as we would call it. So there's our truth table for NOT. All right. So how does that help us in terms of what we can do to compare two values? So again, we have these two values and they're distinct, right? So whatever happens to B, it doesn't matter because it's not going to affect A. So they're distinct values. However, we may want to combine them in interesting ways and say that sometimes what happens to A matters as it corresponds to what happens to B, and vice versa. What happens to B, it may affect what the final output is in regards to A. So in real life, sometimes we say, if it's not sunny and rain is falling, I wear a coat. But if it's sunny but it's not raining, I don't want to wear a coat. So that's an and condition. So if it's not sunny and it's raining, I wear a coat. So now A being it's not sunny and B being it's raining, I need Q to tell me whether I should wear a coat or not. So let's put that back into our truth table. We'll go over here and we'll say, well, A is an input and B is an input, and then we have Q. And A representing it's sunny, so we'll say it's not sunny, or first we'll say, wait, A representing it's not sunny, so we'll say it's sunny and it's not raining, and so we have a, wait a minute, that's wrong. let's come up with a slightly different example because that one doesn't quite fit what I'm trying to do here. Let's go with what can I go with here? Sorry, I'm just trying to look here for an example. Okay, let's try this one. One of my favorite things to eat in the world is cheese, right? So if I'm hungry and there's cheese, eat cheese. So we'll say that A represents, in this case, we'll say A equals I'm hungry, and B represents there's cheese. And so I'll say the A condition represents whether I'm hungry or not, and the B condition represents whether we have cheese. And the Q condition represents whether I'm going to eat cheese. So we can see that if I'm not hungry and there is no cheese, that I'm not going to eat cheese, because that makes sense. There's no cheese anyway, even if I was hungry. So the other condition is I'm hungry, but there is no cheese, so obviously I'm not going to eat cheese because I don't have any. And then the other condition is, and this condition is actually true right now, I'm not hungry, there is cheese in the house, but I'm still not going to eat cheese because I'm not hungry. And then the last condition is I'm hungry, and there is cheese, and obviously in the real world that would also include am I in the mood for cheese. But let's just assume that every time I'm hungry, that cheese is what I want to eat. So I'm hungry, there is cheese, I'm going to eat it. And this, we can see, is an and condition. So if both of these things are true, then Q will be true. Yeah, I'm going to go eat cheese if I'm hungry and there's cheese. And we're going to call this logic an and logic because it just says that if both conditions are true, then the output is true. And it turns out that that is one of our fundamental logic gates, the and gate. And I'm sure that looking over at this list that you'll be able to figure out at least a good number of these and what they do. So we can see now that if I plug these inputs like this, and I go ahead and start this simulation, that A representing I'm hungry, and B representing there's cheese, Q representing I will go eat cheese. So I'm hungry, but there's no cheese, so I don't go eat cheese. And now there's cheese, but I'm not hungry, so I'm not going to go eat cheese. But now I'm hungry and there's cheese, and I'm going to eat that cheese. And you can see that the AND gate satisfies that condition. So it satisfies the truth table that we've created. All right. So what about another condition that we can use to manipulate these two values in some way? Well, another thing that we can say in real life is or. And so let's take this for example. If I'm feeling ill or I have an appointment, I will go to the doctor's office. So, bringing our truth tables back up, we're going to say or. And we'll give our inputs again. And again, we'll list them out as A equals I feel ill. B equals I have an appointment. Q equals I'll go to the doctor. So, for this condition, if either condition is true, then I'm going to go to the doctor's office, right? So if I don't feel ill and I don't have an appointment, I'm probably not going to go to the doctor's office unless there's some other mitigating circumstance that's not considered here. And then if I feel ill, depending on the severity, I will probably go to the doctor. Or if I have an appointment scheduled, of course I'm going to go because I'm already scheduled to be there. And then if I feel ill and I have an appointment, I'm definitely going to go. So that's going to be a 1 as well. And that's an example of or logic. So if either of these conditions could become true, I'm going to go to the doctor. That's going to happen. And so for that one, we're going to use an or gate. And we're going to go ahead and copy these. And we'll connect everything up. And we'll see that this gate will say that if either of these conditions become true, that, yeah, I'm going to go to the doctor. And then if both of them become true, I'm still going to go to the doctor because I'm not going to not go to the doctor if I have an appointment, and I'm certainly not going to not go if I don't feel well. So that's the OR gate. And then lastly, we have sometimes a case where we want it to be only OR and not an AND. And I'm trying to think of a good real-life analog to this one, but it's kind of tough. Let me think. Okay, so I've dug into the depths of Google, and I have found an extremely seedy example of XOR logic, and it deals with a man who has two girlfriends. And then Q equals, I'm in trouble. And so what we're going to see here is this man has two girlfriends, and if he's with his first girlfriend, he's okay. And if he's with his second girlfriend, he's okay. But if he's with both, he's going to be in trouble. And it actually might be that we want to say, I'm not in trouble. Because that way, as long as not in trouble is true, then yeah, we have a representative of an XOR gate. So we see in the first case that he's not with either girlfriend, and in this case, the premise could be true because one of the girlfriends may be mad at him or whatever, so he may be in trouble because he's not with either of them. And in this case, he's with the first girl, so he's not really in trouble. And then in the second case, he's with the second girl, and he's not in trouble unless she happens to be in the restaurant, unless the first girl happens to be in the restaurant at the same time. But then in this case, he's with both of them, and now he's in trouble because they know. So it's not exactly representative, but it's as close as I could really find to what I wanted to demonstrate. So yeah, this is an XOR gate. You can only be with one of them at a time, and you have to be with one of them, or else one of them is going to be angry, and then you're going to be in trouble. So you have to be with one, but not the other, all at the same time. And we're going to pull out the XOR gate, and we will take a look at how this works. So do that. We'll start it up, and we see that if A is 1 and B is 0, then Q is 1. If A is 0 and B is 1, then Q is 1, and then if both come on, Q is off. And that is the application of the XOR gate. And then we have these other gates in here. We have AND, NAND, OR, NOR, XOR, XNOR. And what these other gates are is just the inversion of these gates. So, by example, if we take these gates and slide them down, and then we put up a NAND gate, as its the colloquial reference is. I cannot pronounce that word. I should not even try. So basically, it's going to take the truth table that we have for the AND gate, and it's going to flip it on its head. So we have NAND, and we're going to say A, B, Q. And then the output is going to be exactly opposite of what it would be for an AND gate. So if A and B are 0, then Q is 1. And then if A is 1 and B is 0, then Q is 1. And if A is 0 and B is 1, then Q is 1. But then if both are 1, then Q is 0. And this just says whatever the output of the AND gate is, invert it. So it makes sense that we're just combining an AND gate with a NOT gate to come out with the logic in the end. So we're going to go ahead and start it up and make sure that it performs that way. Both are off. We have Q output as 1. 1 is on. Q is still 1. 1 is on. Q is still 1. Then when both come on, it goes off. And it's exactly the same for the rest. Whatever the truth table is for the gate, whatever the truth table is for the gate, it just gets flipped. And that makes sense based on their names, NOR, NAND, XNOR. So that's what we have as far as the basic gates, and then the XNOR gate is the same way. It just flips the XOR table all the way around. And so how do we apply this to other numbers? Well, we know that we can take a table and we can form a series of operations based on that table. So maybe we should try to apply this to another problem. Let's try to apply it to adding binary digits. And we are going to call this a 1-bit adder. And we're going to say add two digits together. And what we're going to do is we're going to have an A input, and we're going to have a B input, and then we're going to have a Q input, right? Because we're going to take these two bits and combine them in some meaningful way to produce a result. And so as we think of addition, we have A and B as 0. If we add 0 plus 0, we just come up with 0. And then if we add 1 and 0, we come up with a 1. And then if we add 0 and 1, then we end up coming up with a 1. And then if we add 1 and 1, well, wait a minute. What do we have here? So we don't have a 1 because in binary, if we add 1 and 1, we get 2. But in binary, what do we have when we have 2? We have 1, 0. Well, the problem is Q is only represented by 1 bit. Our output is only 1 bit. So Q should be 0. It's the bottom place, right? So if we look at the adder, we have A and B are 0. Q is 0. 1 and 0 gives us 1. 0 and 1 yields 1. And 1 and 1 yields 0. Well, I think this table looks a little bit like this table right here. So we can do what's called half adder addition. So let's stop this. And if we look at this XOR gate down here, we can see that if we say that A is 1 and B is 0, then Q is 1, and 1 plus 0 is 1, so that's correct. And then if we say 0 plus 1, again, we get 1, which is correct. And then if we say 1 plus 1, well, we should get 1, 0, but we can't because we don't have enough bits to represent it. However, we can represent it in another way. And what we can do is we can extend our table to include another bit, and we'll just call that other bit carry out. And what the carry bit does is say that if the addition of these two bits overflows, the carry out bit will be affected. And so we'll say that in the case of 0 plus 0, both carry out and Q are going to be 0. And then in the case of 1 plus 0, carry out is going to stay 0, and then the same for 0 plus 1. But now we have this 1 plus 1, and we're going to end up with the carry out bit set, because now 1 plus 1 is 2. So we end up with the correct value when we add these two numbers together just by adding this carry out bit. So next, we're going to take this, and what you can do is split this into two different tables. So we'll split this on the carry out bit, and Q is over there and carry out is here. And then if we look at this as two distinct tables, now we have the XOR table, and then we have this table. And if we look at A and B being 0, carry out is 0. And if we have A is 1 and B is 0, then carry out is 0. And then if we have the same here, where A is 0 and B is 1, we have 0. But then we have this addition here, where 1 and 1, the carry out bit should be 1. Well, it turns out that this little carry out table actually looks like another logic table that we had up above. And that logic table is the AND table. It works out exactly. So is there a way that we can take the logic gates that we have used so far, and we can build something that can take two binary numbers and add them together? Well, absolutely, yes we can. And we will demonstrate it. We're going to take these two inputs right here, and we are going to feed them to an XOR gate. But then we're also going to put this little sneaky AND gate up here, and we are going to label these two LEDs. We'll label this one Cout, because this is going to be our carry bit. The underscore in digital just makes the subscript notation appear. And then this one's going to be Q, because this is our output of the addition. And we're going to take these two inputs and feed them into the XOR gate, and that gives us the bottom half of our adder. And then we will feed these top two into this AND gate, and that gives us the carry out portion of our adder. I'm just going to compact this a little bit. Okay, so now I'll go ahead and light up the simulation. And we should see that whenever I add 1 and 0, I get a 1. That whenever I add 0 and 1, I get a 1. But then whenever I add 1 and 1, I get 2. 1, 0. And look, it works perfectly. So this is what we would call a half adder, where it adds up, well, this is a full adder, where it'll add two numbers together and it'll use the carry out bit to represent what happens when the number overflows. So this is how we can take a simple bit of algebra and distill it down into something that we can represent using logical operations. So this is pretty cool. This is the basis of all modern computing. And as we go forward, this is where we're going to build our project. And the next thing that we're going to cover is something that we call a full adder with carry in and carry out. And you'll see that in the next video. I hope everybody joins me, and thank you for stopping by.